So this video is going to finish up Chapter 5. Chapter 5 has the last section about two-dimensional arrays, but what never gets discussed by the author of this book very much is string functions. And string functions go along with two-dimensional arrays quite a bit. So we're going to do some two-dimensional array things, and especially with strings, and we will discuss string functions. And your homework will be based on string functions. And then I'm going to do another video that talks about previous homework and discuss it a little bit. Okay, so this is an example of a two-dimensional array. So you can see it's an array of numbers. And the way you define the arrays are by rows. So rows are going this way. Row 0, note that the index starts at 0. So there are 3 rows in this array, and there are there are 4 arrays in this array, and there are 3 columns. So you specify an array by how many rows it has and how many columns that it has. So since we have been dealing with the one-dimensional arrays, you know that you can specify an element by putting the element position in the square brackets like this. So for example, if this was only a one-dimensional array, you would have had x element 0, x element 1, x element 2, x element 3. But we have these other columns to consider also that also have a position 1, position 0, position 1, and position 2. So let's see how we declare that and use that. So here's several examples of declaring two-dimensional arrays. In this first example right here, I have a two-dimensional array of integers. So you have to do these nested curly brackets, but the way it works is this is row 1 and this is row 2. So this array has 2 rows and 3 columns. And I didn't specify the size in this double occurrence of square brackets, because when I did the declaration I made the size by what I was declaring. More proper, of course, probably would be to say here's a character array and it is a 4 by 3. So that's 4 rows and 3 columns. And so here is row 1 of characters, row 2 of characters, row 3 of characters, and row 4 of characters. And 3 columns, 1, 2, 3, 1, 2, 3. Here's another array of characters right here called my words. In this case, I didn't know how many characters I was going to put in each row, or for that matter each column, so I made a larger array. I made it 10 by 10, and then I filled it in with some values, and I didn't use up the whole 10 by 10, and that's okay. And I will talk about what gets filled in the rest of the way when you do this. But you can make an array, whether it's a 1D array or a 2D array. You can make it bigger than what you need, and then you're covering yourself for what you're going to fill into it. So you also have to use like a for structure to output the variables that are in your array. But when you have a 2D array, you have to do nested for loops, so one inside of the other. So taking my example from the previous slide, I have this array called my words. I was a little bit more specific this time. I said it was 4 rows and 10 columns, so that lets me make each word as big as I want. And notice that I can also put my array of characters in double quotes, which is double quotes is a string delineate. It's not a delineator, thing that indicates this is a string. Well, a string is a series of characters. So let me go back one slide for a moment, show the difference. Here I have each character individually in the single quotes, and even though I'm declaring a character array, I can also put all of the characters together in double quotes. This works as well. It's a little bit of a shortcut, but we're going to talk a lot more about strings coming up. So anyway, I have my character array, and I filled in each row with a string of characters. And if I want to output this, I have to do 2 nested for loops. So my outside for loop fills in the rows first, or it says row 0 is, and then you fill in the characters for what row 0 is. Then I go to row 1, and then I fill in the characters or the columns for what goes in those columns. So note, first of all, that it's a nested loop, and then when I want to print out each one of the rows, I am referencing it by the name of the array, my words, and element ij using this notation. So this gives you the row number and the column number. So the first, as I go through the loop, this is held fixed. This is the one that's iterated by the inner for loop, and it puts out the word the for the first time. It actually is putting out 10 elements, because I said to do it till 10, but the ones that we see are T, H, and E, and there turns out to be 7 more elements here, which we'll talk about here in a moment. So this is where I'm going to talk about those hidden things that are in there at the end of a string. So we did a little bit in last week's programming with C-type functions from the C-type header, and those were like get character. We mostly just used get character and is alpha, I believe, were the two that ended up being used for that program where you had to find all of the common characters. There's also a preprocessor header that you can put in called strings.h, and it'll have a bunch of string functions. So C-type has character functions, strings has string functions. So let's talk a little bit more about what is a string. So when you have a string, this is an array that's of characters, and it's stored, and that constitutes a string. But each character that's put in a memory space in your computer will get converted to ASCII, because of course your computer can't really store the letter T. It has to convert it to something numeric, which in turn has to get converted into something binary. So literally in your computer it's storing a binary number, 01110, whatever it is. I cover that in a different class. But so each letter is stored as a number in your computer, including the space, including the punctuation. But at the end of the string is this /0. This is a special character that is added to the end of each string to mark where the string ends. It's called a null character, and the way you write it is a /0. So string is always terminated by a null character, and so technically the length of the string is always greater than the number of characters in the string by 1. But you can use the fact that a null character is put at the end to, well, you'll see how to use it here in a moment. So going back one slide for just a minute, right here, when I output 10 elements in each row, in this outputting of an array. So I output THE, and then I output a bunch of null characters. But null characters don't print to the screen, so you won't see it. So you can use this null character to determine the length of a string. We were determining lengths of an array, kind of a brute force way in a way, looking for the end. But this is another way to find the end of a string. So I have made a character string right here. It says to be or not to be. Initialized a count to be 0 so that I can print some things out. But what I do is I look at each element of the string, and while it's not equal to this null character, then I will increment the count. And so here, after that, I just print what the count is in the end, and it will, oh, I should have put the result here. To be or not to be outputs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It should output 18. Now if I declared my string or my array of characters, to be more than the number of characters that I need. For example, to be or not to be is more than 40 characters. I mean less than 40 characters, but I made the array be a size 40, and I print all of that out. I will actually literally print the 18 characters of the phrase, but then it will print 22 spaces, or actually 22 null characters. Another thing you can do is declare a constant message. Let's say you have a message that you use often. Previously in our programs, we declared constants up at the top of the program in the preprocessor area. You actually do not have to do that. So if I declare within my program, this means constant. So I have a constant. It's a character array called message, and here's my message right there. Notice because it's a constant, I gave this variable name all capital letters, keeping with our coding convention in our class, and Microsoft for that example. So then, one of the things that's kind of nice now is I actually don't have to use a for loop to print out my message. I can just, well, it didn't have to be a constant, but I can print a string right here and print message. So note the use of my %s for null terminated strings. That's what %s can be used for. If I have a string, it's been terminated, as we know, by a null character, and then I can print the string rather than using a for loop to print out a whole message. So you can declare constants, other kinds of constants in your program, like an int constant if you want. Just be sure you declare things with a capital letter. It does not need to be in the preprocessor directives like we have been doing. Something like pi, the number pi, that's a good one to declare in your preprocessor directives, because it might be that pi is used by all kinds of functions and modules and macros everywhere in a giant program that you're developing. But a lot of constants are better declared within your program, or even just within your function, so that they're local only to your function. Okay. So arrays of strings. So this is where we take our string and start considering making it a 2D array. So I have a 2D array called array of characters called sayings, and notice the way I declared it. I have first empty square brackets, and then I have square brackets with a number in it. So this is the row, this is the column, unknown number of rows, but I allot 70 columns to write out the phrase. So 70 columns to write out my first saying here. So you must specify this second dimension, which is in conflict to what I wrote earlier, I think, on a slide. Let me go check that in a second. You must specify the second dimension and make sure it is long enough to accommodate the longest string, including the terminating character. And then the compiler will make the first dimension 3 automatically in this case. Yes, I think I printed something wrong up here. Go back right here. Yes, I needed to have specified that second dimension, the number of columns that I allot here. I can check that. I can compile that in a moment and check that. Or you can check that. Back to where I was. So this is an array of strings, and I have to specify the second length, and it has to be big enough to accommodate my whole phrase. So now this brings us to operations or functions that you can do with strings. If you want to do some string functions, you need to include the string.h header file, and then you can have access to all of these lovely functions of things that you can do with strings. And since your book doesn't talk about them, I'm going to go ahead and give examples of using these different functions, and you will also have homework this week that uses these different string functions. So first thing, finding the length of a string. We had come up with various ways to find lengths of our strings in the last programming, probably last 2 programming assignments. But here's a simpler way. Once you've declared the string.h preprocessor directive at the top, then you can declare an array. Here I am declaring a string array right here. You have to read all my comments. See, programming is fun and challenging. And then when I want to print, I can print one. I could have printed it as a message, but if I wanted to know how many characters were in this string, which was very much like the homework, information that you needed this past homework assignment, I can just say string length and pass in the name of the array right here. So this is a string length function, and it will return the length of the string, and you will find out that there are 37 characters in this phrase. And I think I want to check something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. Yeah, it's not counting I thought it counted the end character, the null. So it's counting 37. Okay. But anyway, this is a good way to find out the length of your string by using the string length function that comes with the string.h preprocessor directive. So you can also compare two strings, but keep in mind that strings are stored in memory, not literally as characters, but they are literally stored as the ASCII, with the ASCII equivalent numbers. So numbers are what are stored in your computer. So I have a string 1 here called the quick brown fox, and I have string 2 called the quick black fox. Here's a little snippet of code right here where I declare the two strings, and I say if string compare string 1, string 2. So I'm going to see if string 1 is string 1 greater than string 2, and then I'm going to print that it is greater than. Oh, you say, how can you tell if one string is greater than the other? That doesn't quite make sense. But what you do actually is that these characters that are stored in memory are stored as numbers, because these are ASCII coded characters. And so you can see that R is number 72 and L is number 6C, that's in hexadecimal. And 72 is greater than 6C, therefore string 1 is greater than string 2. And if you go and look at the ASCII chart, you will see that as you increase in letters in the alphabet, a letter that's later in the alphabet, like R, is also associated with a greater number that's being stored in memory. So you can use this fact to see if something, to put something in alphabetical order, for example. You could put things in alphabetical order just by playing with their numbers, ASCII equivalents that are stored in memory. And so you could use a string compare function to see which one is greater than the other, and you could put something in alphabetical order. You can also see if strings are identical based on their numeric value, less than or greater than, and equal or not equal. So the result of calling this function is a true or a false result. And we've done a lot of tests in our program so far. If A is greater than B, if we're not at the end of the file, then do something. Or while we're not at the end of the file, do something. So one of the things I think was not well brought out earlier, and maybe should be, because I realized that some people didn't realize it, it's not that when you do this comparison, string compare, if this statement is true, you execute the next instruction in the program. If the statement is false, you skip and you go on down to here, correct? But so what is this actually returning? Is it true? Is it false? If you were in C#, the language C#, it actually returns a Boolean variable that's called true. But C is older, and what C does is it returns a 0 or a 1 based on whether the test is true or false. So we can use that. We haven't been thinking about using it very much, but let's look at it. I have this piece of code right here, and I want to do the string comparison. So I have a phrase, string 4, called contains I want to eat pizza. String 5 says I do not want to eat pizza. and then I declare an integer called result. And I do a comparison. And I'm basically saying compare string 4 and string 5 and compare the first 5 letters of it. So I have 3 arguments this time in the expression, as opposed to last slide here there was the 2 arguments that the function was using was string 1 and string 2, but you can also choose to compare the first 5 elements in the string if you want, which is what I'm doing here. So I'm saying look at the first 5 elements of string 4 and string 5 and test. Are they equal? So it turns out that when you do this test, the result of this test is that 0 is returned back to the program if the result is false, and 1 is returned if the test is true. And I want to show you how to use that. So here, let's do the test. The test says, are the first 5 characters elements equal or not equal? If they are equal, then I'm going to print the result. And then look what I did here. I said result equals, and I do that comparison, that string compare function. Oops, I got a typo in here. I fixed that in my code and then I pasted it wrong. Let's fix that real quick. That shouldn't say that to prove the point. Yeah, so I just recompiled this code, but this is what I didn't quite say right. This function, if blah 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 blah, returns a 0 or a 1 based on whether it's true or false. The actual string compare right here does not return a 0 or a 1, but it returns the difference between the two where it differs. And when I ran that program, the string compare, it said that it was not equal. Oops, let me move this over. The 2 strings were not equal, and the string compare result was 19. So we have to go back and look at what the ASCII code is to see why that result was 19. But it's a subtraction of the 2 values of the strings that gave us that result. So the if statement actually returns, the if statement itself returns a 0 or a 1. So I just tested that. It does not return the 0 or the 1 that you can use. So I can't declare int as a result and then make my if statement be the result here. That will not work. If this was a different language, you could declare your result as a true false, but bool as a character type is not recognized by C#, so that does not work. So this statement right here does not work. You can return, you have to actually get the 0 or the 1 that you need for your program later on. Now what I could do is say this statement does work. Result equals string, yeah, you can just have the result equals 0. But okay, so okay, this will give you the difference, and we can look at the ASCII codes and figure that out. And maybe I'll pause for a minute and go ahead and do that so you can see what it really is. So let me pause for a moment. Okay, so I changed my 2 phrases right here a little bit. String 4 is ABC and string 5 is ABE. So E is 2 positions later in the alphabet. So when I look at the ASCII for C and the ASCII for E is going to be 2 numbers higher. So if I subtract the ASCII string for ABC minus the ASCII numbers ABE, this one is 2 letters higher, and the result should be -2. So I ran the program and compiled it, and here's the result right here. And sure enough, when I compare those 2 strings, the comparison result will be -2 because E is 2 characters later in the alphabet. Here is an ASCII table. This is off of Wikipedia, and you can see that C is the number 99. There we go. C is the number 99, and E is the number 101 when it's stored in memory. It's actually stored in hexadecimal right here. So in the hexadecimal system, it's stored as 63 and 65. And so 63 minus 65 would be a minus 2. And so when I do the string compare, you get the result being minus 2. Okay. Which means that was not true. Okay. Concatenating strings. That's our next function that we're going to look at. Concatenating is a fancy word that means that you're joining one string to the end of another. So it's joining strings basically, but you're joining it into all one string. It is a very common requirement of programs to concatenate things together. So you must make sure that your destination array, the space there, is not exceeded. So you cannot, if you try to concatenate string A and string B and your destination is not big enough, you're going to lose information. So the function that you want is called string concatenate function. It requires either 2 or 3 arguments. So off of my C reference chart that I gave everybody in the resource folder, this is how it's talked about. So you either have a string and 2 strings, and you can concatenate them together. I discovered it does not necessarily have to be a constant, even though it said right here it has to be a constant. Or you concatenate up to n characters if you want of the second string onto the first string. So let's try that out. Here is my example. I have a string 6 and string 7 declared. String 6 was 1, 2, 3. String 7 was 4, 5, 6. And then I do a string cat function call right here and print the result. And I thought I was being smart, and I said 1, 2, 3, space, so that it would be correct. But when you have a space at the end of your string, it's the same as a null character to string functions, and my result blurred the two together here. So I said, okay, let's fix it, and I put the space before the 4, and then it was okay, but then I forgot to put the comma here, so I messed up over there too. But anyway, there's how you did a string concatenation of putting one string together with another string. I could store that in a final result if I wanted to. So our next chapter in our textbook is about pointers. But before we actually go to the next chapter, which will be in a different lecture, I want to have a sneak peek at using pointers as it pertains to string searching functions. So at least one of you tried to get a solution for the counting the letters in a user input homework problem by getting it off the internet, and the internet solution used pointers. But you did not, that problem was completely solvable without the use of pointers. But we will now lead into talking about pointers, but I'm going to use finding characters in a string or searching a string as kind of the introduction to using pointers. So a pointer is a variable that stores an address. In this little piece of code example, I've declared an integer called number. Its value is 25. So what happens was the variable name that's called number, the identifier really, is its value is 25, and somewhere in your computer it's stored in memory. And every location of memory has an address. So let's say 25 was stored at 100. Then this variable called number is kind of a label that is associated with this address. Then I can declare this pointer right here, and I declare it by putting this little asterisk in front of it to tell the compiler that this is a pointer. And then I can say, I can get what's in number, or I can get the address of where number is and store it right here. So this is kind of a picture of what's happening. So the variable called p number, so it's a pointer number, it's stored at a different location in memory, but the value that's stored is not 25, but the value that's stored in memory is the address of where number is stored. So that's why it's called a pointer. So this address says what address number is stored at. So it holds an address right here. Okay, continuing on. Oh, and one other thing, that this asterisk right here, which indicates as a pointer, is called a dereference operator. There it is, a dereference operator. Its effect is to access the data stored at the address specified by the pointer. So we'll see here in a moment how to use it, especially in light of our string functions. Okay, so now let's show you how to use a pointer to search for a character in a string, which will be different than how you did it in your homework problem, but this is an introduction to pointers. So I'm actually just going to pull the Notepad, the source code up here in my Notepad++. So here's what I have, a little section of my code that searches for a character in a string using a pointer. So I have a string array declared here, says to be or not to be, called string 8, and the character I want to search for, which I went ahead and gave it a variable name, is n. So now I can say this is a character. I can actually say this is an int as well, and that would be just fine because n is really stored as a number in your computer, right? And so just like the character functions that you could get the ASCII value, the number associated with it if you want, you could declare it as a character or you could declare it as an int, either way. So I'll do it as declaring it as a character. I'm going to look for an n in this phrase. Here I'm going to say the address where the n is located. I'm going to point to it. So I'm going to declare this pointer right here called p got it, p for pointer, but I'm going to initialize it as a null. And then this is the actual line that will search for the first occurrence of that character. So I'll say p got it equals, and this is one of our string functions right here. It's a string character. I'll show it to you here in a moment on your reference chart. So I'm going to look at the string right here, string 8 that I declared, and I'm going to look for the particular character that I'm looking for, which is n. I could have put right here n and it would have worked just fine. I could have done that, but I did it by giving it a label right there. And then I have the statement down here: if p got it, if this is null, this will return a false statement. But if it actually found the character, then it will return the address of where that character is located. So I have a print statement that says the character was found at. The character found was, and then I should put out the character. It should be n right here, and then the parameter at the end of this printf statement is p got it, and it's an address right here. So it points to the address of where the character was found. And so I have a pointer. I need to probably draw a picture. Where's my little pen? Let me get my pen. I'll draw a picture. So I paused for a moment and drew a picture. See, if you were in a live class, you'd have to wait while I drew that picture. So this is efficient doing this. I like this. Well, efficient for you, not so efficient for me. This shows the character array, to be or not to be, stored in locations in memory. So it's stored at a location in memory that starts right here. So the string points to right here. And so then when I found the character, which turns out to be right here. It's going to be the address, this address right here, plus 1, 2, 3, 4, 5, 6, 7, 8, 9. So this address, where this letter is located, is the string address plus 9. So I'm going to show you how you can find that here in a moment, so for fun of it. Okay, so this is how it's arranged in memory. Let's go back to my program here for a minute. So this expression right here actually finds the address where it finds where the first character is, and gives a value to that address. Right here, that address was null. Initially, it was a null, and this expression right here gives that address to P got it. And so, if P got it is not null, then you're going to print character found was whatever, and it should spit it out. And it should spit out where this pointer is pointing. So in my program right here, this is where this initially P got it is 0, but this address where this is located at is at P got it. So I'm going to show you exactly what the address of P got it is in your computer memory in a moment. But first, let's just run this program the way it is. So I will run it. Let me clear my other junk off of here first. There we go. So let's run the program, compile it, run it. And so the character found was N. Oh, okay, not too exciting. You expected it to find an N, right? So I said that when you're doing these, you could work just as easily as an int. So let's put it out as an int and see what it is. So I changed to put out as an int, and it should give me back the ASCII value, just to show you that it does. Yes, so there you got your ASCII value back for little n. I can check that if you would like. I don't think I have that up anymore. I don't have it anymore. So, whoops, sorry. Okay, one more little interesting thing to show you here. I can show that was in decimal. 110 was in decimal. I can show you in hexadecimal if I want by using this format specifier of an X. So let's run that code next. And so ASCII, it's 6E. Interesting. So, and this one I had to look up, but if I actually want to see what the address was, I can put that format specifier in. I don't think your book said that at all, but it's kind of fun to do. So we'll run it one more time. Is that a valid address? Interesting. Okay, so let's try a different character real quick for the fun of it. Let's look for a B. It's a relative address of where the string is. It's not the absolute address. So B is located, well, the difference between these two, if you're counting in hexadecimal, let's not do it in hexadecimal. Let's go back and find this one as a integer, because I can do that math better in my head. $98. So one was 110. Earlier it was 110. B is 98, and N was at 110. 98, 99, 100, 101, 102, 103, 104. Nope, not quite. So we should figure out exactly what that is, because I sort of looked that up at the last minute to see what P would do. Oh, I gave the integer difference in the alphabet between P and N. That's different. Okay, so I wanted the address differences. Okay, so which means I have to work in hexadecimal. So I'll take that off as a different slide rather than going through this program on your YouTube time. So you can output X for hexadecimal, P for the address, looks like it's a relative address to where string is, I to get the integer that's associated with the particular character that you are looking for. I looked it up. So B, this is correct to the pointer addresses here. So B is located at 62, address 62, and N is located at address 6E. But what I failed to consider is the size where each location is stored, i.e. are our numbers stored in 1 byte or 2 bytes. So the difference between 62 and 6E is, in hexadecimal, is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 is an E, so you have to do that math. And that is, so I pulled up my Windows calculator right here. I don't know if you know it or not, but you can change your view to be View Programmer. So now it's in Programmer. I can choose my numbering system. I'm in decimal, but I want to see in hexadecimal because I want to see the difference between the addresses 6E and 62. So I'm going to say 6E minus 62, and that difference is C in hexadecimal, but if I convert that to regular decimal number, the difference is 12. So there are 12 bytes difference in memory between B and N. So 12 bytes, it looks like each character is being stored with 2 bytes. Let's check that. So if I'm here and I say 2, 4, 6, 8, 10, 12, there are indeed 12 bytes between B and N. So when I found out these two addresses, one address was 6E and one address was 62, that's 12 bytes difference, or 6 character storage difference in 6 character storage differences in memory. So on my little PowerPoint right here, the pointer, when it's at P got it right here, that location in memory is, it's actually, you write it in 0x6e is what we found out. So we can just look at the 6e. This just means that it's hex. There's actually more to the address right here, but it's just keeping the last part of the address. The address is actually quite a bit longer than that. So that's at 6e, and this address was at 6.2. So we can calculate. This address will be at 6.4. This one will be at 6.8. This is at 6A, and not everybody in this class probably knows how to count in hex right now, so I wouldn't worry about it too much, but I'm trying to give you some idea that these are stored in different locations in memory, and each one of these numbers being stored takes 2 bytes of information. So 6A, that would be 6C, and that was at 6E. What did I? So that's the beginning. Is that 6.2, 6.4, 6.6? Ah, didn't count right. This was 6.6, 6.8, 6.10, 6A, and 6C, and then this one is at 6E. So hexadecimal is base 16 numbering system. A lot of you already know that, but some of you may not. So we count in base 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it starts repeating. If you're in base 16, you count 0, 1, 2, 3, 4, 5, 6, 7, 8, and I can't repeat my digits, 9. So then we say A, B, C, D, E, F. So base 16 means you have to have 16 unique characters. So there they are. In decimal, this is the number 15. But now I've run out of characters and I have to start repeating. So now the next character in the sequence would be, or the next number in the sequence would be 10, 11, 12, 1A, 1B, 1C, 1D, 1E, 1F. Next number would be 20, etc. So that's the hexadecimal system. I should probably find out who knows hexadecimal and whether or not we need to cover it. Well, it depends on if we need to cover it for our programs. But memory locations are referenced by their hexadecimal values. So that's what I just showed you, that where these things were stored physically in memory. So I was able to give you the address. So this string character function right here looks for the first occurrence of the character that you're looking for. So to be or not to be has several O's in it, for example. So this is how you could implement something to look for several O's using a while loop. While P got it equals, you look for an O in it, and while you're getting an O, you can increment a counter for that. So that would allow you to find how many times the O is located in the string. Well, I was going to run that program and show it to you, finding how many O's there were in that array, and it made an infinite loop. So excuse me, I have hiccups. It took me a few minutes to find why I had an infinite loop. It was actually kind of a silly thing in a way. So let me point out what changes that I made so that you can search for multiple characters in your string, your array of characters. So one thing I did, instead of initializing my pointer to null, I initialized it to the start of the string. So my pointer address now is the start of the string of interest, which is this string up here. This part of the greened out text was in the previous example. I just greened it out because I wasn't focusing on it. So commented it out. So I initialized a counter right now for how many times the letter O occurs in this string array. And then I do have that same while statement, but the place where I made a mistake is I actually want to increment the address. So I want to increment the pointer, so I needed to have that dereferencing asterisk in front. And when I first did it, I was incrementing P got it, but that's not incrementing the actual address that I'm interested in. So I needed to increment the actual address, and then it should tell me how many times O is found in my array of characters. So now if I run it, there was all my troubleshooting in its glory. So I will go ahead and run the program. That's what happens when I left out the dereferencing asterisk. I didn't actually increment the address like I wanted to. So the letter O is found 4 times, and yes, it does actually work. So that's our little introduction to pointers and using pointers, and you could have used that. Now you could use the previous program that we were doing as a homework problem. Now you could use pointers to count how many times certain letters occurred. But you should not have done it in the program submission that you just did. You could have used if statements or a case structure, one or the other, and counted how many times. The last exercise was really an exercise in counting the elements in arrays and also using some of our searching algorithms. So, okay, I see I'm at 50 minutes, which is long enough for a YouTube. I'll make separate YouTubes for the next subject.